In the last video, I gave you an example of an alkene reaction, didn't I? And we went through step by step and we talked about the mechanism of that reaction. Well, now that we know the mechanism of that reaction, guess what? That gets applied to every equation or reaction that we will see from this point on. So let me give you another example. CH2 double bond CH2, and we add hydrochloric acid to this. What would happen? Folks, we just described a mechanism, didn't we? We described some steps. We said, hey, a double bond is here, that double bond is negative, and that negative area is attracted to that hydrogen, and it persuades the hydrogen, come on, you need to leave that chlorine, because that chlorine is very electronegative. And the double bond breaks, pop, away it goes. Hydrogen gets added onto one carbon. A carbocation is formed on the next hand side, and that chlorine, which is negative, is attracted to that positive carbon. Well, this time I'm not going to ask for a mechanism. The only thing that I want you to do is give me the product from this point. All right, so this left-hand carbon has two hydrogens on it. So I'm going to draw those two hydrogens just to say that I can do it. And then over on the right-hand side, this also has two hydrogens. So there we go. There's the two hydrogens that are present. Well, if this reaction happens, sometimes I'm just going to ask you to give me the product, not the curvy arrow mechanisms. So what you need to do is you need to understand that the double bond breaks, away it goes. That opens up two sites of attachment there and there. The first step, this hydrogen is pulled off and it goes onto the molecule to make a CH3 group, right? So I can go ahead and draw that in a condensed structure way. Look, lecture 1 material right there. And then over on the other side, I've got a chlorine, and that chlorine is going to be attached there. Well, from here, I can do a CH2 and a Cl if that's what I want to do. If I want to condense it down, I'm more than welcome to do it that way. So there is the product formation of your first alkene reaction with an acid, and in this case, HCl. Well, guess what, folks? It happens no matter how complicated the molecule is. So let's say that we have a carbon with two methyl groups and a double bond. And here we have a methyl group on top and a methyl group on the bottom as well. But this time, let's add HBr. Guess what? The steps are the same. Once again, I told you, you learn a procedure just like nomenclature, and you apply that procedure over and over every single example that we have, because there is no way to memorize millions of different reactions. We just can't do it. No one does that, right? That's craziness. So here we have a double bond. That double bond breaks, so I'll erase it. I'll get two new bonds that will form. I've got room just to draw them straight out to the left and right, and that's what I'm going to do. Who cares where they go? So hydrogen goes on to one carbon, and Br goes on to the other carbon. And look, you just did your second organic reaction. Nobody said this was hard, but do you believe that people really do have trouble with this kind of stuff? I mean, it makes no sense. All right, so here let's go to number 3. I see an alkene, and this time it's in a ring. I don't care. I don't care if it's in a ring, because it's going to behave the same way every single time. Isn't that what I just said? Well, okay, so if it's in a ring, so what? There's a double bond that's going to be there. We're going to erase that double bond, and we're going to draw a bond here and a bond there. Hydrogen goes on one, so we'll put them on one carbon, and iodine goes on the other, so we'll put it on the other. There you go. That's all there is to it. Look how easy and seamless that was. You probably didn't have to think about it after that first example. You just kind of knew what to do. All right, well, here's the problem. You knew it wasn't going to be this easy. One of the reasons that it was this easy is because if you go back and take a look at some of these examples, you're going to see, here, let me change my colors. I thought I did, but I didn't. You're going to see over here on the right-hand side of this, two hydrogens here and two hydrogens there. So it's a very symmetrical molecule, wasn't it? It didn't really matter where we put the hydrogen and where we put the chlorine there, because no matter if I put it on the left or if I put it on the right, we would have ended up with the same structure. The same thing would have happened down here in the second example. Everything over here to the left was the same as everything over on the right-hand side. Again, a very symmetrical molecule. It didn't matter where I put the H or where I put the Br. And then finally down here with the cyclohexane ring, or the cyclohexene ring, same kind of deal. It doesn't really matter because there was a hydrogen here, a hydrogen there, and a group that was the same as the group over on the bottom side. So this was a very symmetrical molecule. These are the easy ones, right? They are the easy ones because I don't have to think about this type of problem other than the fact of splitting this molecule in half and realizing this goes on one side and this goes on the other. That's all that we did. But you know good and well, these molecules are not going to stay this way. You also know that the examples are not going to stay this simple. It's a very good way for us to introduce the concept, but later on, and we're going to quickly see some of these in some of these reactions, we're going to see problems with where these groups go on and what order they go on with. All right? So, for instance, if I do pull hydrogen off of this compound, well, which one of these carbons in the double bond does it go to? Does it go to the left-hand one or does it go to the right one if it is not symmetrical? And you're going to actually see in some cases neither one of them. That's where the problem lies. So what seems really easy right now is going to turn a little bit trickier later down the road. Oh, okay. I kind of see where this is going now. So before we go further, let's go back and take a look at some nomenclature rules. So let's look at this one. 2 carbons in a long chain. So this is an F and it's an ENE because there's a double bond there. Here, 1, 2, 3, 4 in a long carbon chain. So this is bute and this is butene. And it looks like on carbon 2, I've got a methyl group. And it looks like on carbon 3, I also have a methyl group. So 2,3-dimethyl butene. Well, this is a 2-butene, isn't it? So I need to make room in there. So let me write that a little bit better for you. So 2,3-dimethyl 2-butene. However, based on the way it's drawn, I could maybe talk about cis and trans and E and Z, right? So it looks like that's the template. Well, not too fast. I can't really talk about cis and trans because the carbon to the left has no hydrogen and the carbon to the right has no hydrogen. So cis and trans, no good here. I can't compare hydrogens on that molecule. I then go to E and Z and say, okay, well, E and Z is going to be able to work. Well, if I look at the 2 groups that are here to the left, they're the same. I can't compare them. I can't rank one as a higher priority than the other. So this also does not have E or Z because those groups are identical. A methyl on top, a methyl on the bottom, and then over on the right-hand side, can't rank those either. It's the same group over there as well. All right. Then finally, down here at the bottom, this is a cyclo, and it's a cyclohex, and it's an ene because there's a double bond present. I don't have to do the one. I could if I wanted, but it's okay. It's understood to be there. That's the very first carbon of the cyclohexane ring. Okay, so I've just named the reagents here, right? Ethene, 2,3-dimethyl 2-butene, and cyclohexene. But I can also name the products at this point. I mean, we've learned this. This is kind of our module 3 information. I told you it was cumulative. It was a build-up process, right? So if I go through and name those based on the alkane nomenclature, I can do that without an issue. Here I see a 2-carbon long chain. So this is ethane, right? It's an ANE because it's an alkane. And then on carbon number 1, I see a chloro group. So 1-chloroethane. I start numbering here to the right because out of these 2 choices, that is where my substituent or my attachment is, and that's the closest end to it. All right. Here, longest carbon chain, well, it's still going to be a 4. It was a 4 before. It's still a 4 now. We've not elongated a chain. We've not changed the number of carbons at all. So this is a butane because it's an alkane at this point, all single bonds. It looks like there's a group here that I have to name. That's a methyl group that showed up in the original. It's going to show up in our product. It also looks like here's a methyl group on this carbon, but it also looks like that carbon also has another group as well. There's 2 of them on that carbon. So most of the substituents are on that side, which means I need to number closest to that side. So here is the end of the longest carbon chain. So this is going to be carbon number 1. That's carbon number 2. This is carbon number 3, and that's carbon number 4. So there is a directional to this now. It wasn't there in the beginning, but it is now. A direction to numbering the chain. So on carbon 2, I have a bromo group. And then on carbon 2 and on carbon 3, I have 2 methyl groups. So 2,3-dimethyl butane. And that's it. No more. I don't number the single bond because they're all single bonds. I only number double bonds at this point. So 2-bromo, 2,3-dimethyl butane is going to be the name of that product. And then finally down here at the bottom, I can name this one as well. This is a cyclohexane because it's a single bond all the way around. And because it's a single bond all the way around and they're all hydrogens and they're all carbons, iodine is really the special one at this point. So we're going to give that one as carbon number 1. So this is iodocyclohexane, or if I wanted to, I could put a 1 there. That's not a big deal. 1-iodocyclohexane. So all of the information, this is what I'm trying to get across, all of that information is coming back. Every bit of it. Lecture 1 material talking about structures and talking about Lewis dot symbols and polarity to predict reactions with. Lecture 2 talking about acids and bases, but that was the first time that we started drawing curvy arrows, if you remember back then. Lecture 3, as far as alkanes go and naming alkanes, all of that can be brought into these types of questions. And then lecture 4, all of the nomenclature with the alkenes and how to name those and a little bit of their structure and stereochemistry as far as cis and trans and E and Z and the way that they're ordered. All of it can come together in one major cumulative problem. That's the problem that people have with organic. That's because they don't get it weeks and weeks ago, and now they're forced to understand and assume it, that they do know it. And organic will tend to get worse as we go on throughout the semester. But I'm going to prevent that from happening. I'm not going to let that happen to you, am I? No, because I think that if you've done your job and you've watched these videos and you've done these assignments and I stay just on top of you as far as doing stuff all the time, then I think you are in a much better position of learning these reactions. And the further we go in this semester, you're going to be okay. I know that you're going to be okay. All right, so let's turn our discussion on something else before we do more of these. What if these things are not symmetrical? What if they're not even? The 3 that we just did were. Well, this is where we start pulling information that we've also brought into the picture weeks ago in other lecture modules. If they are not even, we question the carbocation that can be formed. Remember a couple of modules back, we talked about carbon that carries a positive charge. And we said this was a carbocation. There's 3 different types. There is a carbocation that we call primary. And that is a carbon that's attached to only one other carbon. And then after that, it can be anything it wants to be. Well, we also had secondary carbocations. So these were carbons that had a positive charge, and maybe on one side a carbon or another side there's a carbon, but it's attached to two others, at least. It's attached to two other carbons. And off of each one of these, da-da-da-da-da, and here, da-da-da-da-da, it can be anything it wants to be. Doesn't matter. But that is a secondary carbocation. And then finally, we talked about tertiary carbocations, which were carbons that were positively charged, and then off of that carbon, we have three bonds to three other carbons, typically, especially here in the very beginning. And then off of each one of these, it can be anything they want to be, so I can write R groups here instead of doing the da-da-da-da-da. Maybe you like that better, though. I don't know. So primary, secondary, tertiary. Tertiary carbons are going to be the most stable out of this category, right? The reason is because this positive charge is positive, but look, this carbon brought buddies to the bar. This carbon bought some friends. Bought friends. It maybe so. It could have bought friends, but it could have brought friends as well. Maybe both. But it brought friends to the bar. And those are kind of like bodyguards. This is how we described it back in the day. They're bodyguards that kind of cover up that middle carbon and buffer it in a way so that other things do not see the positive charge as well. It's still there. Things can still see the positive charge. But those friends help protect that carbocation. And the more friends you bring, the less chances of that carbocation getting in trouble. Okay. So tertiary carbocations are more stable. Primary carbocations, they're the least stable out of these three. As you can imagine, they don't bring too many friends. They're looking for trouble. They're going to go to the bar, and they're going to get a little rowdy, and then there's no one there to really take up for him or her when they get into that position, and before you know it, they're getting handcuffed and wheeled down to the police station. That's a primary carbocation. It gets in trouble. It gets in trouble very easily, and things can go in and pick fights with that carbocation without a problem. So out of these three choices, primary, secondary, and tertiary, these reactions that we're going to start discussing, they're going to, number one, create a carbocation. We know that. We've just talked about it. This is typically our very first step of the reactions. Hydrogen goes on, attaches, and the carbocation is formed that will then attract the nucleophile to come in and attach to that molecule. However, we need to keep in mind that a carbocation does form, but we need to look at all choices, and we need to choose the most stable out of the options, especially if the molecule is not even. Now, I want you to keep in mind, I'm going to write this in a different color. No carbocation is stable. When they form, they're not going to stay around very long. Do not misinterpret that. No carbocation is stable. They are not going to stay around. They're always going to go away. However, out of the carbocations that I can choose from, there is a ranking of stability. And tertiary is more stable than secondary, which is more stable than primary. That is the order. That is the ranking. 3 greater than 2, greater than 1. But out of those choices, if I looked at them as a whole, neither one of those are going to stay around. Neither one of those are going to survive. At the end of the night, they're going to get into a fight. At the end of the night, they're going to get destroyed. And at the end of the night, something is going to happen to them, no matter what. It's just how big of an attitude are they going to bring to that bar before they pick the fights with people that they don't want to pick the fights with. Now, with that said, we're going to do some examples. And what do these examples look like? Well, they look like this. This is kind of the first. This is really the first, I would say, before we do reactions at all, you're going to have to be comfortable answering this type of question. And this question is going to say, okay, list the following carbocations in order of decreasing stability. Okay, so what they mean is that they want the most stable, and then they want you to work yourselves down to the least stable. That is decreasing stability there. All right, so the way that I answer these types of questions, I'm looking at carbocation ranking. Tertiary, greater than secondary, greater than primary. And I look at A and I see this carbocation and I look at it and it's attached to three things, right? Three things right there. Well, this is a tertiary carbocation. This middle one, that's a carbocation there, easily identified. There's a carbon to the left and one to the right. There's two things attached to it, so this is a secondary. And then here, the carbon that's last, this is a carbocation easily identified, and it's only attached to one other carbon, and that's the one to the left, and that's it. Notice I don't count hydrogens, and this is a primary. So this one, good news, it's already in order. The tertiary is going to be more stable than the secondary, which is going to be more stable than the primary. So tertiary is the most stable, and my primary is the least stable. And that is in order of decreasing stability. Most, middle, least. All right, now let's look at B. If I look at B, they're trying to give me a trick. They are testing me and wanting me to go back and remember certain lecture topics that were presented earlier on. And in this case, electron withdrawing groups. The reason that I say that is because, look, here's a carbocation. That carbocation is a CH2 group, and this is primary. Here we have another carbocation, and that's primary. And here we have another carbocation, and that's primary as well. I can't use that to make my decisions. Those primaries are all regarded as equal. So I've got to use other things about the structure of the molecules in order to rank these. Well, what's different about them? Well, what's different about them are the attachments that's onto the molecule. So here I've got a chlorine, and here I have a CH3 group, and here I have an F, which is a fluorine. Well, what's different about those? Electron withdrawing? Electron withdrawing, yeah, or electronegativity. Electronegativity for fluorine is the highest out of all the atoms on the periodic table. What would come next would be the electronegativity for chlorine. And then what would come last would be the electronegativity for carbon that's involved in the methyl group. All right, so how do we rank these in order of decreasing stability? Okay, so decreasing stability, stable means it stays around. Guys, I don't know about you, but if I had fluorine that was extremely high in electronegativity, extremely negative, and then we have this positive piece on it, something's going to happen. Right? Fluorine is going to scavenge to try to find any electrons that it can. It's already electronegative. It's more prone to be negative anyway. And then we have a positive that's next door to that. As you can imagine, this positive and this negative is going to react. There's going to be some attraction. There's going to be some destruction that begins to happen here. Versus that of this methyl group, which is just a carbon. This is just a carbon. That's just a carbon. The electronegativities of these are really not that much different. So this carbon's like, yeah, you're positive, but you know what? I don't really care. Where this fluorine is like, gimme, 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 gimme. So if we are to rank these in order of decreasing stability, this one is going to be the most stable. That's because there's not an electron withdrawing group. There's not anything that's negative that's out there that's on it that will cause the destruction of that carbocation. This one will stay around longer. Even though, in the long run, in the big picture, none of these are stable, this one would stay around longer versus the other two. All right, well, chlorine, of course, would come in second. Chlorine does have some higher electronegativity value. We do see some negatives. We see some positive. We see some attraction. We see some destruction, but not like this one. So hopefully these three problems are okay with you. Right now, this is really the focus. It's going to be the major focus before we go further in reactions. It's one of those things that if you can't do this, again, you can't predict those products. And this is going to be the downfall of you if you are not comfortably picking out the proper carbocations to form our products with. So this is where this video is going to stop. And in the next video, we'll pick up from this lecture topic and we'll continue to move forward and we'll get closer and closer to really working out the reactions the best way possible.